All right. So if you recall what we have discussed yesterday, right? We discussed a functions, which is a uh, previously non-existent. Okay, so we define a function which are later is turn out to be a log functions, log with some base. Later we will try to identify what the base is. Okay. Okay, and let's see. Where is that thing? Okay. Okay, so we did some we discussed some properties and uh, examples problems with especially about the derivative and integrals. Okay, and we discussed yesterday. The last thing we did is a thing that we call the logarithmic differentiation. So let's just review stuff. The last thing we did. Okay. All right. So let's move to this one. Okay. So the problem is, let's see here. E, mm, this is the problem. Okay. So it's kind of complicated. Not really difficult because we know we have to use the product rules. There are the quotient rules inside. But the thing that makes this complicated is because there's multiple of those. Okay, so this is what we called earlier logarithmic differentiations. Okay, so this is y. So we deal not directly with y, but with the log of y, ln of y. So here, ln of y is ln of those stuff, okay? And by properties of ln, okay, remember that we have three properties mostly, namely, first, if you have exponent, such as like this, right? This is also exponent because this is square root is exponent 1/2, okay? So each have exponent. You can take exponent out, okay? Factor those exponents out. And then product becomes addition of ln. And then divisions like this is a quotient, is a difference in ln. Okay, so using those, we see that this becomes, okay, let's take 2/3 out, okay, and ln the rest. Okay, and then because there's a product, then this becomes addition of ln. So it has a exponent 2, so take the 2 out, ln 3x plus 2. Okay, you have a quotient. So you mean that you have a difference, f negative minus uh, that's power 1/2, exponent 1/2 because that's the square root. Ln x plus 1. All right, is that clear? It's clear. All right. And now we take the okay. When you take ddx, recall that y is a function. So in computing ddx of ln of y, you use a chain rule. Okay, so ln, the derivative is 1 over. Okay, by chain rule, you have y prime. Okay, so this is the difference. And let's see, take the derivative of each of the terms in right-hand side. Okay, that's easy. So you have 2/3. You have just put everything in the inside the ln to the denominator, okay, and the derivative on the numerator. So derivative of x squared is just x squared 3. All right, here we have 2, 3x plus 2, the derivative of 3x plus 2, that's this is 3. And this is a 1/2 x plus 1, derivative of x plus 1 gets 1. Okay, so then y primes now the this term, okay. So just 4x, okay, plus 6 over 3x plus 2 minus 1 over 2 plus 1, like this. Then multiply by y, which is there. Of course, you can extend y as this one here. Okay, so this is what we mean by logarithmic differentiations. Right? Questions? Okay. So let's do some other thing. What about the graph of Ln? What's the graph of Ln looks like? Okay. All right, because x is see that. Okay, let's plot this thing. We know that the what a phi fact Ln of 1 is 0, so that's the x-intercept. Okay. And then let's take the derivative. F prime is just 1 over x. All right, because x is positive, then 1 over x is also positive for all x. X positive. So it's going up, increasing, increasing, monotonically increasing. And so this sign chart for so it's positive all the way. And second derivative is, now it's easy. No, because the form is minus 1 over x squared. So this is negative for all x. Positive. That's all negative. Okay. So according to the shape, okay, plus minus. Remember, the shape is increasing, but with a concave down. So it has the shape like this. Okay. All right. So, and the thing is, there is quite a few things to do. It's in the problem of exercise that I just mentioned here. That limit as it goes to the right, far to the right, is infinity, and limit 0 from the right, okay, is negative infinity. Okay, so the graph going to be something that looks like this one. graph looks like this. So this is y equals ln of x. Okay, so increasing. Yeah. Okay, so far that's what our log function looks like. Okay, so the problems now, how do we uh, what is the base of this log? Okay, what is the base? Okay. Um, let's see. Okay, we'll deal with that later. All right, so the next section would be, all right, so um, as I mentioned a few weeks ago, that the operation or functions in many functions operations in math comes in pairs. Means we're trying to get the inverse of this log. Okay, so how we do that one, do the things. Okay, so we have to define what we call the inverse functions. Okay, all right. Recall that the if we have a functions, the functions from an say interval, and we say that f is 1-to-1, or sometimes I call it injective. If for any x1 is not equal to x2 in E, the image are not equal. Okay. Or equivalently, we say that uh, if we have equals to this in the image, then you cannot avoid that x1 must be equal to the x2. Okay. All right, so 1-to-1, and in a Venn diagram, it looks like something that looks like this. So this is different stuff from the above, so it has to go somewhere else. For example, here, it has to go not the 2. That, that's 1-to-1. Okay. Okay. And um, we say that say K is surjective if every y in J there is an x such that equals y. Okay, so everything's in the codomain, sorry, everything in the ring should have a partner in the domain. Okay, this is not the case. this one in particular, because you see that you have three points here, three y's, which doesn't have any partner in x. So this, it's rejective. Okay, so f is bijective. If it is ejective and surjective at the same time, simultaneously. Okay, so this is bijective, surjective, and injective. Okay. All right. So what we know so far is that if you have something like this, you just restrict the codomain to the range. Okay, if this is ejective, then f is actually bijective. So uh, the codomain is restricted to the image. Okay. So the nice thing about bijective is that it has a inverse. Okay. So if you start with f, this is bijective. Then you are able to define what's the inverse. Okay. Okay, so what is inverse? Inverse means that if you start with x here, map it with f, right? And this f of x, and pull it using this inverse. Okay. Then you get x back. That's for every x in the domain. On the other hand, if you start with y, okay, y here, uh, you're using inverse, so you're pulling y to x, and then map it back using f, and then you get y. So that means a inverse identity. Okay, so that's an inverse. So let's see. Example is that um, we know that increasing function has a I to j is increasing. Then it is ejective. All right, so why is it true? Well, increasing means x1 is increasing means if you have two comparable things, x1 is less than x2, for example, Then if you map them, it is still true that this is f x1 is less than f of x2. Right? So this is what's increasing. That means if you start with a different stuff in I, x1, not equal to x2 here, then you have different things on the map. Okay. Okay, so that's why it is injective. Okay. Okay, so if you restrict to the to pre to the image, f is bijective. Therefore, okay. All right. Further, now with calculus, if f is differentiable, then we know how it's increasing or decreasing. Okay. So in the field of calculus, uh, if f is differentiable and has the sign positive, then x or x all f is increasing. Therefore, is injective. And therefore, oh, I should mention that this is also true for decreasing. The it's okay. It's also injective. It's two. Then the other way around. All right. So this is how do you know a function is has inverse or not if you have differentiability. So let's do some example. Okay, let's pick up some example from the book. So show you the theorem. If f is strictly monotonic on its domain, that means either increasing or decreasing for the whole domain, then f has an inverse. Okay, so let's pick up some problems. Let's see. Where is that thing? Okay, where is? Okay, so let's pick up something like this. Fx of x power 7 plus x to the fifth. Okay. Okay. Let's see. This is polynomial, therefore differentiable. therefore differentiable. Okay, so let's say let's take the derivative. Okay, so that's easy. Both give you let's see, this is always positive. Okay, so this is zero except all right, it may be zero at x equals zero. Okay, so you see that this function has a okay, or okay, so let's say, so because the difference it is not monotone. Yes, sorry, it's wrong. It's always positive except at zero. Okay, so you see that this is a increasing functions. Uh, sorry, how should I? It can be zero. Let's see. Let's see. It's increasing. Let's see. In fact, this is increasing also on the negative. Let's see how to see that thing. Oh, okay. For x non-zero. Okay. And the sign chart should be positive here, positive here. So this is increasing, this increasing. And because it's continuous, you should be able to continue this one. You connect them. Okay? So it's monotonically increasing. Therefore, what's injective? Now, the way to compute uh, the inverse might not always easy though. Okay. Mark. Computing inverse may not be easy. Some are easy, some are not. Mostly are not, like this one. Okay. And here's difficult because you have to somehow so if you able to solve x equals something in term of y, then you have inverse able. But in these things, it's looks like it will you won't be able to express the x as a function of y. Nevertheless, uh, the inverse exists. Okay, y exists, yeah, because it's monotonically increasing. Okay, questions? Okay, so let's do something more than that. That is what we call a inverse function theorem. Okay, that is to say, if a inverse exists, uh, it is differentiable if we start from a differentiable functions. Okay. All right, so this is the theorem. What it says is that if we start with the differentiable functions, strictly monotonic in on I, that means strictly monotone, so either it's increasing or decreasing, but in both cases, it's injective, and therefore, inverse exists. Okay. Okay, if the derivative is non-zero at a certain x, some x, okay, uh, then f prime is differentiable. Sorry, uh, f inverse is differentiable, and the derivative at x at y here is you can compute by just 1 over. Okay. All right, so let's compute that thing. For example, let's see. We want proof this thing. Let's take an example of this. Um, so let's see. Okay, here we have this the functions. Okay, because it's polynomial of order 5, that is not easy to find x in terms of y. Okay. Um, so it's computing f inverse explicitly is not easy. So let's find this one. F prime is 5x to the 4th plus 2. Okay, it's plus 2, this is always positive. Okay, so this is for x real numbers. Therefore, then f is increasing. Okay, therefore, objective inverse exists. Okay, therefore, cannot be computed. I would say directly here cannot be computed. Computed explicitly. Let's see. Oh, in this case, yeah. But you have to solve x from so how you get the inverse expression of inverse. All right. Okay. So what we get here is that we know it's increasing, therefore exists, and we're supposed to compute. But we're supposed to compute derivative of the inverse at point 4. Okay. So how we compute derivative if this is unknown. Okay. Problem here is that to compute if we cannot find let's say cannot find f inverse explicitly, right? Okay, so the inverse function theorem IVT says that, well, you compute this way. Derivative at 4 is 1 over derivative of f at, well, this is what we need to find out. Okay? Because what happened is that suppose b equals f of a, we what we compute here is that the derivative of inverse at b now, right, is 1 over f prime of a. Okay, so this is not f, not the same. This is b, and then this is the a. How is related? F of a must equals b. Right? So in this thing, we need to find. Let's see, what is f of something equals to 4? Okay, so that's the easy thing. Not easy, but if that's a problem, usually that's something you can find easily. All right, so if this is supposed to be 4, then you see that it's easily x equals 1. Or, no, this is 1. Okay, so this is 1 over f prime of 4. I'm sorry, f of 1. And if you compute it directly from here, you plug in 1, this is 157. Okay. Any questions? Questions? Okay. So far. All right, another example. Problems. Oh, I should mention that uh, let's see, the graph of the inverse. The graph of the inverse is, let's see, when you're in high school, do you recall how to get the graph of the inverse? For example, this one here, number one. It is a monotonically increasing, therefore it has inverse. That's how you get the graph of 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 the inverse. Recall a way how to do this one.
I forgot about it, sir.
All right. Basically, when you try to find inverse, you switch x and y, okay, and you solve the y, solve for y. That means if you switch x and y, that means geometrically you are reflecting the graph with respect to this diagonal y equal x. Okay, so where is that thing? Cannot find the color. Okay, so if you reflect this, you get something that looks like this. Okay, so this is the white f, while the blue one is the, okay, blue one is y equals f of x. Okay. So just get the what you call it, the image or reflection. So you put the mirror here at y equal x, the diagonal. Okay. So that's how you get the inverse. So example. Where is that thing? Okay, let's do this one here. Okay. Right. Okay, looks like complicated, but let's do this one. All right. F is given as a integral. Okay. All right. So first thing is that let's check this one. F prime. It should say explicitly check sign of F prime. Okay. So you compute F prime. So by the fundamental theorem of calculus, so derivatives just wipe out the derivative just wipes out this integral. Okay, because this integral, the lower bound is constant, upper bound is just the variable x. So the derivative wipes out the integral. So you get only this 1 plus cosine square. Just replace the t by x. There we go. All right, so because what you have here, cosine squares is a non-negative, so at least 0, but you add 1, so make this positive. Take the square root, and then you always have this positive for any x. Okay, that means this is monotonically increasing. Monotonically increasing. Okay, and therefore ejective. Then inverse exists. Okay, and the question is that find so a derivative of inverse at a. Okay, so let's see, but a is, let's see, a is the image of pi over 2. Okay, so the by inverse function theorem, it is a 1 over, and see, what is this? F prime at pi over 2. Okay, so let's compute that one. So if you plug in pi over 2, this is 1 plus pi over 2. Cosine pi over 2, that's 0. Okay, this one is 0, this is just only 1, so that's it. Okay, so that's when you get 1. Okay, b, derivative at b, again by inverse function theorem. And let's see what number is mapped into b. Let's see, this is 5 pi over 6. That is going to be so if you compute that, all right, so what is 5 pi over 6? So that means 30, 30, 150 degrees, 150 degrees, 150 degrees. Let's see. Okay, you can check the calculator. 150. Okay, so then this gives you this negative of, if this is 1, this is 2, this is, oh yeah, this is 1/2, negative 1, so positive 1/2. half. Only the cosine, I should say. This is not the sine. Cosine, this is square root of 3. By negative, because this in the uh, second quadrant. Negative 3 over 2. 3 over 4. Right, so this is 7. Okay. Right, so this gives you 1 over. So 2 over. Yeah. Okay. And C 0. Right. So you have to, again, by inverse function theorem. All right. So what is map to 0? So the question is, if this should be 0, and what should be the x? Can you see that one? Recall what the integral means. Integral from 0 to x. What does it mean? What does it mean geometrically? Integral from 0 to x of something.
Is it the area under the curve from 0 to
Area.
x?
Right, so area. When is area equal 0? The thing is, this is positive, right? So always positive. And area, but area is 0. So nothing below the x-axis. Area, because this is sine area actually. So you have a negative also if it is below the x-axis. But this is nothing below x-axis. It's always above the x-axis. But the area is 0. So what is x?
Is it
So
also
why is the
0?
reason? Nah, that's it. Because the upper bound would coincide with the lower bound. So that's the only thing that makes the integral equal 0. So the upper and lower bounds coincide. So x must be 0 also. So that means x must be 0. So that's by inverse function. So this is also 0. Okay. 0 is 0. All right, so let's need to compute f prime of 0. The 0 cosine 0, this is 1 squared 1, so square root of 2. Okay. If you okay. All right, any questions? If not, then let's take a break here and then start in 5 minutes. So, okay.